Hello, everyone. This is Marina, a pretty nerdy person that wants to share the topic of quantum entanglement. That is really interesting. It's freaking out the minds of modern scientists because they cannot really understand what that means. And I feel that it can really bring a revolution in the way we think of ourselves, of nature in general. And this is a presentation that I did for an exam that is not really scientific, so it's gonna be hopefully understandable for everyone. So I want us, before starting with the presentation, let's have um, let's look around us. And sitting in this room, how we are used to think is that every object is independent of the object that is next to them. So they are connected only if one acts upon another. And this is how we perceive our macroscopic world. Uh, We would never think that, for the way we have been raised and thought, that objects that are really distant from one another can have instant effect on each other. And this is exactly what quantum entanglement is. It says that two particles that, or whatever we want to call it, two waves, two points of space-time that have interacted in the past, in some cases will be considered as a whole. So they cannot be considered separately. So even if they are from one point, like in opposite points of the universe, they will be connected instantaneously from some correlations that still we don't know where are they living. So let's dive deeper into this. This means that in the macroscopic world, that is the world in which as humans live, we are used to think in a deterministic way. And this deterministic approach is encoded in the Newton laws that are the core of classical mechanics. And basically, they state that if I don't apply any kind of force to an object, then if it is at rest, it will stay at rest. If it was in motion, it will keep moving with constant velocity. So the movement itself of the object is not is dependent only on the forces that are acting in its causal surroundings. What does that mean? That if, for example, I call a friend of mine and I'm like, yo, what's up? And I want to ask him or no, I tell him something funny, then he will receive my message only after a time that is equal to the ratio between the distance between me and my friend and the velocity of the signal of the phone that is traveling. And it cannot be that uh, something happens before this time. He receives this signal before his time. And this is also the core statement of special relativity, relativistic mechanics that was developed by Einstein. Now, what we need to change in our perception is when we dive into the behavior of the microscopic world, that is light, uh, the matter that is around us. Like when we study in the micro scales, we can see here a graph that says like the smaller, then we need to pass from classical mechanics to quantum mechanics. The faster, then we need to pass from classical mechanics to relativistic mechanics. But the thing interesting here is that in the macroscopic world, there is nothing such as definite position or a definite velocity. There is only probabilities of different states. That's um, really completely different from how Newtonian mechanics works, no? Because if we have, for example, we want to describe the position of a particle, in classical mechanics, we would say, okay, it is in, I don't know, in 3 dimension, that is how we are used to see the world, then it will have 3 coordinates, x, y, z. In quantum mechanics, the particles don't have a definite position. So they are described by an infinite sum of many, many different states. So they are everywhere in every instant of time. Only some values are allowed, but they can be infinite. And what we use, we will see later, is the wave function. That is that encodes basically the probabilities of having some state when we measure it. So before the measurement, we have no idea what is going on. I mean, we kind of know because we can predict it with the laws, with mathematics, but in the moment in which we observe it, the value that comes up is completely random in one of the infinite possible states. So we see that, for example, here in the bottom right corner, in classical mechanics, we can treat, for example, an atom, that is the component of matter, as a nucleus put in the center or something, with an electron orbiting around it. But in quantum mechanics, this description falls down because we are not talking about particles with some position, but we are talking about waves with different probabilities. So we will have something more like in the figure on the right. So we will have regions where it's more probable to have the particle when we measure it, and regions where it's less probable, but still it can be anywhere. So it's not bounded by some specific value. Okay, before diving deeper in entanglement, I want to give some really basics on quantum mechanics. And I can start by the most important thing, that is the superposition principle. So we see that this guy psi in the first formula is the wave function. So it lives in a complex space. So that's not really important, but like an extension of the real numbers that we use. And the most important prediction of quantum mechanics is that if two states, let's say position equal to 1 and position equal to 2, are solution of the equation describing the system, then also the sum of these two states is solution of that equation. So this means that we can describe the state of one single particle, as an infinite sum of different states. And in front of each one, we put a coefficient that in this case is called the secant with E, sorry. And that coefficient is related to the probability of that state. So as we see here in the graph in the top left corner, we have, for example, infinite possible position of the particle, and then the square modulus of the wave function that we were talking before, that is just taking basically the multiplication of it with itself, complex conjugate. Then we will have the curve of probability for each position. So we see, for example, in this case, that it's indicated the most probable location because there is more probability. So this is how in quantum mechanics the systems are treated. And what about the measurement process? Then the measurement process means to make the system interact with some instrument. So it can be also our eye, like this is what happens every day, no? So we have, for how quantum mechanics describe it, we have this crashing of waves that lives in every point of the universe at the same time, and they interact in so complex ways. And then when we are here, a consciousness that acknowledge these objects, then they manifest as only one thing. And this is what we see, what we call reality. So how is this encoded in quantum mechanical formalism? We have a quantum object, C. We decide what we want to measure of it. So we say, okay, let's measure, for example, the position or the velocity, or we can also measure the energy, the spin, whatever. And we set the instrument so that it's gonna measure that specific property, and it pops up with a certain value that we call small a. What will happen is that that object will stay in that state. So the wave function before observing it collapses, it says, to the state corresponding to that value that we found. And this is an irreversible process. So it means that once some quantum object that is just like a really small thing, let's say, for so far how we can understand it, is measured, then it will stay in that state. It will no longer go back to the superposition of many, many different states. And this is basically the main difficulty, let's say, to understand quantum mechanics, to make quantum computation or whatever. Because after you extract the information from that system, then it's gone. It's only that thing. And yeah, as we said before, the probability of measuring one specific state is given by this formula that is the product between the wave function before observing it and after observing it, square modulus. And we find, yeah, there was like 30% of probability that this value came out. Yeah, I will not talk about quantum decoherence because it's a bit too complex, but it's basically the fact that the state that is in a sum of many, many different possibilities, when is interacting with an environment or just is perturbed in some way, or even without, just letting it evolve, then it will decohere. And that is why we see the macroscopic world as we see it, because we don't see, for example, this pen being in all the possible position it can get, because at our scales the wave function are no longer a coherent sum of states, but they pop up just like 1. Okay, so now we are ready to give the mathematical definition of entanglement, and it means entanglement is happening between two states that are no longer separable. So the general case of separable state is when we can say, okay, this particle is here, this particle is there, they are independent from each other. They will not, the change on one will not change the other. When this is not the case, so when the change of one will affect the other, then we say that the state is inseparable or entangled. So we can make also one quick example, that is the qubit, because it can be interesting for the future. A qubit is a superposition, so sum of state 0 and state 1. In bit, that is the normal computing, we have that one state can be either 0 or 1 with some probability. Now, the thing of qubit is that it can be 0, 1, and the superposition of both with any kind of coefficient. We just need to have that the total probability is 1. So we will have that the square modulus of alpha plus square modulus of beta will be 1. But they can evolve and acquire any kind of superposition. So the states are infinite. And in the case of two separable qubits, as we can see on the left, we have that the state of two qubits is described as the multiplication of the state of the two qubits. While in the case of entangled qubits, that is when they are not separable anymore, we have, for example, this is an example of entangled state that is called Bell entangled state. It is a superposition of 0 for the particle A or qubit A and 1 for the qubit B minus 1 for the qubit A, 0 for the qubit B. As we can see, they are no longer independent. But if, for example, we measure that the qubit A is 0, then we know that the qubit B is 1. So they are connected in this mathematics, let's say, because if one is this is the function that describes how the system of the two particles behaves, then if one is 1, then the other one is 0 and vice versa. And this is at the base, the core thing of entanglement. Okay, so seen like this, it would look like, okay, but what does that really mean? We can make an example that is the most famous one. That is the case of two friends, Alice and Bob, that have a system of two particles. Again, particles can be of any kind, the particles of light, the particles of matter, any kind. It's just that we are considering single excitations, single waves. We have these two, this system with these two qubits that has the state as seen before. Okay, so they are entangled. But what does that mean? Let's say Alice takes qubit A and Bob takes qubit B. Of course, they don't know which one is one. It's just that we use these names to describe it. And they separate each other far, far away. Then Alice measures the value of if it's 0 or 1, that value, no? And she gets 0, for example. Then she's like, okay, I got 0, then maybe Bob has 1. she doesn't know for sure. She calls him, so she uses signal traveling, and it's like, yo, bro, what did you get? And he's like, yeah, I got one. Okay, interesting. Then they repeat this with other 2 qubits new, because as we said before, after you measure it, they will be in that state forever, or at least if they're not, blah, blah. And then they do this for many, many times, and they note what is the values that they got, and these values are random for them, no? They are just measuring 1, 0, 0, 1, 0, and after some time, when they finish, they call each other and they realize that there is instant connection. So if she measures, for example, 0, Bob measures 1, and vice versa. And this is instantaneous. So this is the the feature of quantum mechanics that was really, as we will see fastly later, was really not liked by Einstein, because he was like, okay, but that means that there is not locality. So we cannot, for example, consider a system that is closed and independent from the other universe, because it will be depending instantly by other objects that it interacted with. And he was so against it. So it took some time to realize that actually it's not that they communicate, because there is no signal traveling between them, but in the core, in the mathematics describing them, they are dependent on one another. Let's see how they got here. We can say that the paradox uh, was treated mostly starting from 1935, when Einstein, Podolsky, and Rosen wrote a really famous article that is called "Can Quantum Mechanical Description of Physical Reality Be Considered Complete?", where they raised this exact question that we were talking about. So they were really cautious in their affirmation, and we will see in detail. Then there was this theory proposed that will say, okay, let's say that they both have one definite value before being observed, and this value is hidden somewhere. It's just that we don't see it, but there is even before we observe it. But then they found out that it cannot be for some stuff. So we will understand this a bit quickly. But before, I want to just to mention that this in physics, the conservation laws are really, really important. They are a consequence of deep properties of nature that arise from considerations of symmetry. So, for example, the conservation of linear momentum, so the movement of an object, depends on the invariance of translation. And the conservation of energy depends on the independence of time. So we could interpret this kind of instant correlation by just a need of that physical system to respect symmetric laws of symmetry. And then one thing that is really, really interesting for me is that in quantum mechanics, for example, position and momentum cannot be measured at the same time with arbitrary precision, but they must be, as we see in the bottom right corner, the uncertainty on the position x multiplied by the uncertainty on the momentum that is related to the velocity p must be more or equal to h over 2, where h is called the Planck constant and is one of the most important constants in quantum mechanics because it defines the minimal amount of energy. Like, for example, the energy is given by h multiplied by the frequency. So it's the unit of quantum action. So this is called the Heisenberg uncertainty principle, and it states that some observables are not compatible, so they cannot be measured together. The knowledge of one will interfere with the knowledge of the other. And for example, energy and time are two of these. And yeah, this is important for understanding what comes next. So let's go to the Einstein-Podolsky-Rosen paper. So the authors started with a really old and interesting question, that is, what is real? If we think about it, there are many definitions of reality. So they said, okay, we can say that something is real when we can predict with certainty its value without perturbing the system in any way. And then they are like, okay, so if we have a theory that describes reality, then we can say that this theory is complete when every object of reality that we can predict with certainty is described by the theory. And then they consider two entangled particles or photons or whatever. And they say, okay, so we separate them and then we measure on system A the position. So we know with certainty the position of the other. And then we measure the velocity on one system so that we know with certainty the velocity of the other. And then they're like, but then it means that both velocity and position as a reality. But quantum mechanics do not describe them together because they are not compatible. So quantum mechanics is not complete. And then we're like, no. It cannot be that the measurements done on one side of the universe affects the reality on the other side of the universe. It just cannot be. It's not possible. How can this happen? This is what is called locality principle, that says that any action in one point of space cannot influence instantaneously a point at distance t, but it must take this time t equal d over c. That is what we were saying at the beginning. No, I call my friend like, yo, bro, I need to wait some time that this signal reaches him. But these correlations happen instantaneously. How do we get out of this? Einstein was really scared of this theory because that would mean that no closed systems, there were communications faster than light. Then it was understood that it was not like this, but at first it looked absurd. And it's famous his sentence saying, um, do you think that the moon is not there if I'm not watching it? Or God does not play dice and all that stuff. So he really didn't like this spooky action at distance. So this slide will be just mentioned because it's really similar. It's an experiment that was uh, thought by David Bohm, and he was really a genius in this kind of stuff. And it was like, okay, so we consider just non-compatible observable of a system with two objects that are entangled, and we see that there is instantaneous connection. So it was just an experiment to prove this. Um, so then the only two possible explanations that he could give is either we have non-local phenomena, so we have a correlation instantaneous between different points of space and time, or trying to save the situation. Maybe there are some variables, as we were saying before, no? Maybe there are some variables that are hidden. We cannot really understand where they are, but every particles knows already what it has to be. So there is not communication in that moment. It's just encoded in some hidden variables. So he developed this hidden variables theory that was uh, welcomed by the community at that time because nobody wanted to leave the locality principle, let's say, because it makes things really complicated. But then John Bell uh, says like, no guys, I'm sorry, but we need to consider non-locality. So John Bell, that we can see in the picture, in a really clean and elegant way developed this inequality that we see, and it says, okay, so if the world is real and local, as we are used to think in the microscopic world, then this inequality must be true, where these factors are correlation functions between different ways of measuring. It was just um, they are developed assuming that the world behaves in the realistic and local way. And then they test quantum mechanics prediction and they see that they don't respect the inequality. So basically, either the world is not described by quantum mechanics and it's local and whatever hidden. But if we want to take quantum mechanics as a valuable theory, and we should, I guess, because it's really giving so many explanation of stuff that was not understood at all before, then it's not local. So we have this continuous and really complex merging of many excitations of, now it's gonna sound weird, but this is quantum field theory that is like quantum mechanics 2.0. It's like an ocean of probabilities, and basically the excitations from the void that are me, you, this laptop, whatever, are not depending only on the surroundings, but they also depend on the states of particles, so other objects that they interacted with in the past. This is really not immediate to grasp, no? Because we cannot imagine in the way we've been taught that um, we can have connections at distance. So now, to conclude, uh, this exam that I gave was like an exam on philosophy, so there are some philosophical questions, but really, it's Mm, I'm studying quantum mechanics right now, and I feel that this is one of those core phenomenon that may really change the way that we see the world. This is still not understood at the level of one, two particles, but is witnessed. So it would be really interesting to expand this concept to everyday life. For example, I observe something, I think about something, I talk with some people. This is an interaction. So, what does it mean that I am entangled? This may sound freak or something, but it's true, like we are made of particles, we are made of light. Our brain is quantum mechanical. We think in a way that is really similar to what I explained before and what is quantum mechanics. We process many, many different states of excitations between our neural networks that can be in infinite states, no? Each one with some probability, and the probability of it is given by how we've been raised, mm, all the environment that surrounds us. So, yeah, for now, there is a deeper understanding of this, but we need quantum field theory that I don't even know. I'm studying right now, but I hope this was interesting. And yeah, maybe think about these questions that I will not read. So, thank you for your attention and have a nice day.